All right, welcome back. This is the last example of this episode, and it's going to focus on the motion of a pendulum, specifically the tangent function. So yes, I did find an application for tangent, but the other ones were kind of a stretch. So, all right, let's get started. A pendulum hangs from the roof of a moving car. Move my camera. When the car accelerates, the angle of the pendulum from the vertical is modeled by a tangent function. And we can see this in the diagram. So on the left is no motion, and then you can see the direction of the car motion is to the right. And when that happens, the pendulum swings to the left. And in red is like the vertical that the problem refers to. And we're given the tangent function, so tangent of theta is ma over mg. So mass is just, m is the mass of the pendulum, a is the acceleration of the car, and g is just a constant, it's 9.81. There's a whole derivation for this, but I'm not going to do that. So let's go ahead and answer this first question. What is the domain of the function? And we want to consider the context of the problem. So we also want to consider not only the context, but the tangent function itself, and if it has any limits to it. So I don't know why it always does that. Let's recall that tangent of theta is the same as sine of theta over cosine of theta. And let's think about if there are any places where this function would not work. So anywhere that cosine of theta equals 0, first of all, it's going to be bad. And we know that happens when theta equals pi over 2, 3 pi over 2. That's it if you're just going from 0 to 2 pi. And that's just kind of a concept of rational functions. The bottom can't be equal to 0. Everything else is fine. So, well, we know that those are the only domain restrictions for just the tangent itself, but now let's look at the problem. We can see that the angle can go in one of two directions, and it's blocked by the ceiling. And so I denoted it here, but let's say to the left of the vertical, our angle is positive, and maybe to the right of the vertical, our angle is negative. So we can say that the domain of this function, the pendulum is going to swing anywhere between negative 90 degrees and 90 degrees. Because when it reaches right here, if at all, that's the next question. If it's right here, then that's at an angle of 90 degrees. And it could do the same on the other side. But we know that it can't equal 90 degrees because tangent of 90 degrees or pi over 2 is non-existent. So we'll say that theta is between negative 90 degrees and 90 degrees. Because the car could change directions. I mean, we don't know. So that answers that question. Part B, what is the period of a tangent function, and how does it compare to sine and cosine? All right. So you might already know what it is, but let's go ahead and pretend that we don't, so we can explore this a little bit. And the best way to determine this is by looking at a graph. So we got our graph right here. Okie doke. So it just says a tangent function, so we don't have to use the one in the problem. So let's just say tangent of theta equals y. And like we said, we know that theta cannot equal pi over 2. 3 pi over 2, and so on. And we also know that because this is technically a rational function, we know what happens when the bottom equals 0. If the bottom equals 0 at a certain point, then there's going to be a vertical asymptote at that point. And so that's just a concept from Math 3. So let's go ahead and label this. Let's say this is pi over 2, and this is 3 pi over 2. And this is 0. So we're going to have asymptotes right here. All right. And then I always like to think about when it crosses the x-axis, because that's just a really nice point to work with. And so that's going to happen when the top of the fraction equals 0. So sine of theta equals 0. We know that happens at 0, pi, 2 pi, and so on. So we have a point here. Let's say pi is right here, and 2 pi is right here. So let's add that to our x-axis. So pi and 2 pi. Okay, and I said I was going to kind of explore, like, you know, you get to this point, where does the graph go? And so because we have these vertical asymptotes, we need to consider what is happening to this cosine function as we approach the asymptote. So as the angle is approaching pi over 2, if you think about the unit circle, and I'll do it in yellow. So we're approaching pi over 2. Our x value, our cosine for the unit circle, is getting, that's a bad pi over 2, is getting smaller and smaller and smaller. And so we have a really small, really small positive number on the denominator, and we're going to have a positive number in the numerator, which means you're going to end up with a really big positive number. So as we approach pi over 2, our cosine function is also, I'll just write it like this, it's approaching infinity. So that's what our graph is going to do. And then it kind of goes off like that. Same thing here. And you'll notice that when we're approaching it from the left, which is right here, it goes positive. If we're approaching it from the right, it becomes negative. And that's, again, dependent on the unit circle. Don't worry too much about that, but it's just because cosine is, if we're approaching it from this side of pi over 2, then cosine is negative, so you get a negative number right here. Again, not super important, but good to know. All right, so it's just going to keep doing that. And so our period is going to be this segment right here, which is a length of pi radians. That is different from sine and cosine. I'll just circle it over here. Sine and cosine, the period is 2 pi radians. So a little different. All right, let's do part C, and we'll do part D in a different part. That was kind of redundant. So can the pendulum ever become completely horizontal? What happens to acceleration as the angle approaches 90 degrees? So can it become completely horizontal? No. And the reason is because if it were horizontal, we already talked about this, the angle would have to be 90 degrees, and that is undefined for tangent. The next part of this question, what happens to acceleration as the angle approaches 90 degrees? We saw this in the graph. So we can actually write this as a limit. I don't know if I've really done that, but I'm just going to show it to you, and then I'll write it a different way. So as this angle approaches 90 degrees, so that's what this is saying. So what happens as the angle approaches 90 degrees? Well, the function goes to infinity. So we write the function right here. So let's write it as, we'll just put tangent of theta, it doesn't really matter. Okay, it approaches positive infinity. And again, that's like, technically you would want to do, I think it's like put a plus. Hold on. That's from the left side. So you would put like a minus right here to show it's from the left side. I realize I'm doing things that probably don't make sense. Basically, we're just going to use the graph to figure it out. So we see that as our angle approaches 90 degrees, our acceleration is going to go to infinity. And that's because we would be dividing by a really small number. And actually, we wouldn't have to even worry about this side right here because our domain is from negative 90 to 90. So it doesn't matter. So yeah, that would be how we would write it in limit form. But just remembering that acceleration is our y-axis in this case, and theta is the x-axis. Okay, I will see you back here for part D.